Okay, so with no further ado, I'll introduce Peter Reid, who will talk to us about the potential air quality effects.
Okay, this is working? Great, let's get started. So this presentation is really all about you, so we're going to try and make as much time afterwards for answering your questions. This is a very complex report. It's very dense reading, and so what I'm doing here is I'm boiling it down to its essentials, but there's a lot more information in the reports that you can access, and I'll make reference to some of these, but I'm going to try and give you a walk through how we did our work and what we found, and then I can answer your questions. So I'm the discipline lead for air quality for this project. I led a team of approximately 10 people at various times, worked on this project. I didn't do all the work myself. We had people doing modeling. We have meteorologists on staff. We have people who just reviewed the reports and the work for quality. They just came in as a quality step. So all in all, about 10 people touched the project over the last 4 years, and we've gone through several iterations of modeling this, and we've learned a few things along the way that led to improvements in this, the final product. So without further ado, our section, if you boil it right down, our section of the EA strictly looks at air quality. We examine measurements taken locally in and around the Kamloops area for the last decade or two, and we compare those to the government objectives for air quality. Tells us, are they above, are they below? There's about 7 substances we look at. There's about 10, 12 different standards, and we compare them to the standards to say, is air quality good? Is it fair? Is it poor? And how does that change throughout the year? We also look at a prediction of the mine's effects, both around the mine site in isolation and then in combination with what's happening in the city. And we've done that by using a computer model. I'll describe that a little bit later, the CalPUF model, and how we did that. And we did the same thing with that information. Like once the computer model puts out the predictions of what's happening where, we can analyze that data the same way that we analyze air quality measurements from monitoring stations. We get a prediction for every hour of every year that we model, and we look at them in exactly the same way. We're talking about air quality here, and we're just strictly talking about measurements and predictions as they relate to these objectives, the standards. They're just basically a ruler. Is it taller than this? Is it smaller than this? It's just strictly comparing the number, the highest number, to the standard. And we don't talk about human health in our section. We're fortunate in this big of an assessment. We have a separate team that strictly looks at human health. The information we give them helps them assess what is the inhalation risk. What risk do we have from inhaling various things that are in the air already from the city, and what is the project's added effect, and what does that do to change human health? We also feed them with information on dust deposition and metals in dust and other compounds that are included in the diesel exhaust. So that information is done by us. We do the work, and then we pass it on to the human health people. The human health people, they do their assessment. So Brian Lease down the hall, he's the guy to talk to about how does this all fit? How does air quality and dust deposition eventually relate to human health from all different routes: inhalation, ingestion, dermal contact, and in foods, country foods. So that's the guy. Brian's down the hall. So in our terms of reference, we narrowed down the focus of our study to looking at these compounds. The main one we're interested in is PM 2.5, or particles smaller than 2.5 microns in diameter. These are very, very fine particles. They get right into the respiratory tract because they're very small. They can go past the nose and throat. They don't get caught up in the nose and throat, and they have a respiratory effect. Health people agree that this is the thing that we should be looking at in terms of human health effects. And so that's why it's our prime thing. It's what we're focusing on tonight. We also looked at 3 gases: oxides of nitrogen, oxides of sulfur, and carbon monoxide. And those are combustion byproducts. They come out of every furnace, every truck exhaust, industrial sources, and the trucks at the mine emit these things. So we looked at those, and we also looked at larger particles. We looked at total suspended particulate, which is very large particles. And we looked at dust fall, and that's the stuff that falls on your car about 3 seconds after you finish washing it and falls on your deck. So we looked at dust fall and how much of that falls out in the city and around the mine. What we found, in short, is that the whole assessment boils down to trucks on roads. There's a lot of there's about 23 or so very large trucks that are hauling ore and waste rock from the pit to various areas in the mine. The ore goes to the facility for processing. The waste rock goes to waste rock management areas, waste rock dumps. And these trucks traveling on the roads, that both have emissions from the exhaust, and by just traveling down the road, they raise dust on the road, and there's PM 2.5 in that dust. So the amount of dust you get from a road is governed by the size of the truck, the speed of the truck, and then the length of the road. All other things being equal, if you have a road that's 5 kilometers long, it's going to emit twice as much dust as a road that's 2.5 kilometers long. So the whole assessment boils down mainly to trucks and roads, but not to trivialize the other parts of the project. The pit has emissions, so do the waste rock storage areas. They have emissions because there's dumping going on there, and the tailings storage area. The tailings storage area can also have emissions. When you get a high wind, for example, you'll get emissions off the tailings storage area. So we consider all these in the model, but the most important ones are roads, trucks on roads. So, short piece about the dispersion model. We used the CalPUF dispersion model. That was the model everyone told us to use. BC Ministry of Environment recommended that. That's the most sophisticated model in their suite of models that they recommend for this particular use. The United States EPA, they approved that model. And Dow Stain and Bruce Ainsley wrote a paper for the CAPA, and he also recommended the use of the CalPUF model. So everyone's in agreement, this is the model to use. And we run it with a worst case scenario. So what we do is we study the mine plan. We try to understand when is there going to be the most emissions from trucks, and when is there the most amount of waste rock and ore moved by trucks. So we took 2 years, year 4 and 8, because they both have interesting features about them. One has the most truck traffic, the most material moved, and then the other year has material being worked on close to the city. So we didn't want to choose a year where activities were happening far away from the city, but we also wanted to choose a year where there was a lot of material being moved, because every year there's a different amount of material being moved based on the mine plan. So year 4-8 is our worst case. So we modeled that year, and we assume that year is happening all the time, that the worst case occurs all the time. We also modeled what's called a base case. The first time we did this, we simply modeled the mine, and then to get a cumulative assessment, you add what's called background. You take a measurement locally and you just simply add that one number. And we looked at that and we thought, we're really not getting the full picture, because we're not understanding how the mine and the city interact on an hour-by-hour basis. We're simply adding one number to a very sophisticated result. So we convinced them, when we do this again, let's model the city and mine separately, look at them separately, and then combine them to understand how the mine and the city interact on an hour-by-hour, day-by-day basis. So that also allowed us to do some quality assurance, where we could actually look at the predictions the model puts out and compare that to measurements in the city that we have, historic measurements. So we can understand how is the model reproducing what is known about air quality in the city. So these are the three cases we looked at. Like I mentioned, the base case is the city of Kamloops. We modeled all the activities that happen in Kamloops. We modeled all the industrial emissions, went to the ministry, got all the permits. We went to the National Pollutant Release Inventory. We got the quantities that these industries are reporting. Some industries provided us with more specific information so that we could accurately reproduce their facility. So we modeled about 7 industrial facilities from Lafarge out to the pulp mill. We did Tolko, Heffley Creek, the kitty litter plant on the reserve. We also modeled home heating emissions. So from Environment Canada, we got their emission inventory of heating emissions and traffic emissions from trucks, cars on the roads in the city and out of the city. We threw in modeling landfills, because landfills are areas that just emit dust, like because there's traffic on them, there's people dumping things, there's movement, so there's dust. So we modeled the Owl Road landfill, the Domtar landfill, the City of Kamloops landfill, and we modeled those all as separate layers so that we could study them individually and then put them together to get the whole city. And I'll show you a kind of a neat output that we get by doing that, where we can attribute effects in different parts of the city based on this layering of the model, building it up in layers. The project, the lone case is simply that, it's the project. So we have all the various parts of the mine, the pit, the roads, waste rock storage, tailings, and the processing facility, and we have them in the model, and we model it as if it's the only thing around and there's nothing else going on. So we understand how the mine operates in isolation. And like I said, the application cases where we just mathematically add the results hour by hour, receptor by receptor. And you'll see some graphics that kind of explain this. A lot of arm waving going on, but once you see the graphics, it'll become intuitively obvious what we've done. So this is the emissions in the city. The PM 2.5, on an average year, 681 tons are emitted. 50% of that is from industry, and about a quarter each from transportation and road dust. So that's dust that's been stirred up by vehicular traffic. Very small amount from transportation, about 2%. And land disturbance, like agricultural land, that's a very small number. So these are our emissions of PM 2.5, and then when we run them through the model, we run through 3 years, about 26,000 hours to model the city. One run took us 11 days, and we have a pretty high-powered computer. So one run took 11 days, and this is one of the products that we produced. And what this is the worst 24-hour period in 2003 at every one of the receptors. We got about 15,000 receptors in the model. So this is the worst 24-hour period at all of those receptors superimposed on one graphic. So this isn't happening on any given day. This point here can be March 31st, that point there can be April 27th, this can be January 12th. So it's an amalgamation of the worst thing happening everywhere all at once. And you can see some things right away. Highest concentrations are on the valley bottom, the valley floor, downtown, North Shore, some little clusters up here in Sahale, Aberdeen area. Outside of the town, you can see a little bit of stuff happening along the Trans-Canada Highway and Highway 5. And this is New Gold right here. That's New Gold's operation. Higher concentrations in the valley floor and the city center, lower concentrations on the periphery of the city, because there's less emissions as you get on the outside of the city. And really good air quality here. We've got some measurements from around Goose Lake, and the air quality there is virtually pristine. So we studied this base case, and then we compared it to measurements to make sure that the model's performing well, and we're really happy with the model performance. The model replicates a lot of the things that we're seeing in the measurements. Higher concentrations in the winter than in the summer, higher concentrations in the valley bottom than in the higher parts of the city like Aberdeen and out east and west of town. So the model's behaving fairly nicely. We're pretty confident that it's doing what we want. This is this layering I was telling you about. What we're able to do is we've extracted results from 6 kind of arbitrary points in a north-south line. so that we can study what effect does each of our source contribution groups have, how much does it contribute to the total. And number one is up at the mine boundary. This is near the pit, but this is just the base case, so there's no mine active here. Number two is the city development boundary. That's the height of land up near Coal Hill. Number three is the nearest residence in Aberdeen. 4 is about Mid-Sahali. 5 is the west end of the downtown. And 6 is in the North Shore, where we see some of the higher concentrations. And to this, we've added a number. Since we're not able to model sources outside of our modeling domain, that's about 70 kilometers wide and about 55 kilometers high, we add a number to all of our results that's representative of the air coming in. What does the air coming in have in it in terms of PM 2.5? And we've agreed with the ministry that number's around 3.8 for this. No, I think it's about 5 for the 24-hour average, sorry. So we've agreed with the MOE that this is what we can assume about what's coming into the city before anything happens to it, coming off the Pacific Ocean or smoke from forest fires or whatnot. And this is the green stuff here. This green is what's coming from the outside of our modeling domain, and it forms a majority of what we're seeing at sites 1, 2, and 3. These are the city sources. That's heating, that's road and rail emissions, heating, and the red is industrial. So the city doesn't have a whole lot of effect outside there. It has a little bit more of an effect at location 2. At location 3, the city is responsible for about maybe a third of what we see at location 3. And at 4, this blue thing here, that's home heating and heating at businesses, space heating in general. So 4, 5, and 6. So half of the PM 2.5 on an annual basis that we see in the North Shore is from heating. Very little from industry. I showed you before, industry emits half the PM 2.5, but there's only this little tiny sliver is attributable to industry. What's happening there? Well, industrial emissions come from about a dozen or so well-designed stacks at various facilities around town. That stuff goes up into the air where it's dispersed, and by the time it reaches the ground, it's fairly low concentration. So it's engineered to perform that way. Why is heating such a big deal? Over here, here, and here, heating is a big part of the picture. Well, you saw in the previous thing where we talked about how much emissions are. There's about 4 or 5 times more PM 2.5 from furnaces and space heating than vehicles. And think about where your furnace is, where the exhaust from your furnace comes. It's like 5 meters off the ground on top of your house. Now the furnaces don't emit a whole lot. Natural gas fired, maybe a small percentage of wood, but mostly natural gas fired. But in a city of 85, 90,000 people, there's about 50,000 furnaces. There's about 40,000 furnaces. And they're all in the city and they're all near the ground. And every workplace, every store is heated as well. And this is most pronounced in winter. So we allocated the heating emissions to the colder parts of the year, and there's no heating emissions in the summer. Transportation emissions, surprisingly small effect. The project case. Like I said before, a project is mostly about roads and vehicles. Over 50% of the emissions are from the roads alone. And there's a large amount from ore storage areas. That's because they're being worked. There's trucks traveling there. They're dumping their loads. They're moving on. The tailings have some emissions. And the pit itself, there's activities in the pit. A lot of movement, trucks, blasting once a day at noon, and just loading of ore and waste rock into trucks. So those are all sources, but the big one is roads. 352, so about half as much as you see emitted in the city of Kamloops is emitted on the mine site. And that's the effect of the mine. So when we modeled the mine, this is what we got. The pit's about here, And we know that the winds prevail from the south, southwest, southwest, sometimes westerly. So that's why this big blob is pushed away from the mine, the pit source and the roads. The winds were from the north, that blob would be down there somewhere. So again, this is 24-hour PM 2.5. Important thing here to notice, it's fairly constrained in this area, and it barely touches on upper part of Aberdeen. So this is a mine all by itself. There's no background added to that. There's no effects of the city added to that. So then we put them all together. And that's the city plus the mine. So you see this blob around the mine has grown in size, mainly because background has been added to it, and the effect of the city has been added to it. And the city here looks much like it did in the previous slide. And I put those two slides, the base case and the application case, right next to each other so we can toggle back and forth. And you can just see what areas the mine influences and what are unaffected by the mine. So there's before, after. And you can see that there's a line kind of right around Aberdeen Drive where the effects are really pronounced in this area and they're really subtle in that area. And that's because when we model the project alone, you can see that the project's effects didn't go that far into the city. And this is the same analysis we did before on an annual average basis, but this is the same analysis we did before where we're able to compare one case against another. So in this case, we're comparing the base case, which is the blue, to the project case, which is the brown. So at location 1, which is right on the edge of the mine, about a third of what we're seeing at that location is from the mine, and 2/3 is what is already there, largely from background, but a little bit of a contribution from the city. You go up to the city development boundary, it's less than a quarter of what's in total there, is less than a quarter is from the mine. This is the nearest residential area in Upper Aberdeen. It's about 6% increase above what's already there. And then at these three locations throughout the rest of the city, that little tiny speck there is what the mine contributes. So when we look at this, we say the only place where we have a chance of actually measuring the effect of the mine is right up here in Upper Aberdeen. And there's a monitoring station put there about 4 months ago. So we stand a chance of actually detecting the mine there and being able to differentiate mine effects from urban effects, just based on the wind direction. Elsewhere in the city, we don't have a hope of actually finding the mine in the measurements in the rest of the city. It's such a small contribution. We looked at the citywide average, and the citywide average is about 6.4. So if you take the entire city as a whole and you average all of these numbers, it's about over 8 or 9 in here, and it's around 4 or 5 there. When you average them all together, after the project, it's going to equal about 6.4. 0.15 of that is the effect of the project, the mine. That's about 2.3% increase. So we can stand to see a 2.3% increase if you average it over the entire city. More in some areas, less in other areas. Year to year, PM 2.5 can vary by about 14%. So that's just natural variability you see from one year to the next. So this number here is about a sixth of the normal natural variation you see from year to year. One year isn't like the next. You see trends in PM 2.5 that are kind of driven by global patterns. Could be weather, could be sources upwind, luck of the draw, what have you, but not every year is the same. So we see natural variation of about 14%. So the mitigations that we assume when we're running our model, we've assumed that certain things are happening on the mine site. Our early runs of the model, we saw some really high PM 2.5 numbers, and we said, you know, this won't fly. You've got to do more about those roads. So they agreed to a much higher standard of mitigation for the roads. And we reran the model with a more stringent mitigation applied to roads, and those numbers came down because they're the biggest contributor. They're also going to have to do things like managing the tailings storage facility and what we call the tailings beach, because there's going to be fine sand on this beach. Now, while that's not being disturbed by trucks, it can be disturbed by the wind. So they're going to have to mitigate that to a fairly high extent so that we don't get a lot of emissions off of there. So mitigating the roads, mitigating other features like the tailings is going to solve a lot of their issues. We haven't specified how they mitigate them. We're very careful to do that because we want to allow them the freedom to use one method or another and to find the perfect mix of mitigating measures. If we said they're going to use water in there and they wanted to use chemicals, they wouldn't be doing what they said they were going to do. If we said you're using chemicals, that eliminates water as a mitigation. So we've given them some freedom by saying you're going to achieve this level of control on these features, and they get to choose the way in which they achieve that level of control. Monitoring and management post, like when the project is ongoing, there's 2 monitoring stations that have been installed. There's one to the southwest of the mine. That's kind of upwind. If the winds come from the southwest, being to the southwest of the mine means you're upwind of it most of the time. So there's a station there now. It's been there for about a year. It's measuring what's existing. So they'll be doing that on an ongoing basis so that after the project goes in, we can say, has the project affected that monitor at all? Are we seeing any differences that we can attribute to the mine? The Aberdeen monitor, I mentioned, that's there. That's a cooperative monitor. The city and the company are collaborating on that. And that, should the project go ahead, that monitoring station will stay there, and it'll be a KGHM funded monitoring site in Upper Aberdeen. Really good place for it. The ministry's decision, but they will probably want a 3rd station, which will be downwind, exactly downwind of the mine, which will be kind of around the Knutsford area. So we'll probably see one there. These monitoring stations, the beauty of them is that you can access that data 24 hours a day on the internet. You can go onto a website, you'll be able to see what's going on. So if you notice something, it's windy or something, you saw some dust, you thought it was from the mine, you can go and look at their website. It's pretty easy to understand. Wind's coming from here, you look at a map, monitor's there, the wind's going this way, PM 2.5 goes up, that's probably a mine effect. So that's going to be part of the ongoing management. They'll be able to study those results and say, where can we do better? We've had some kind of an event where we caused some dust. What caused that? How can we go back and fix that? So it's kind of an adaptive management thing. We can learn from the model. We learn a lot by doing the model, but there's also going to be, in practice, getting better at managing dust. This is something they have to do. They're next to a city. The other thing we're doing is we've given our model to the city and to the Ministry of the Environment. The Ministry of Environment has asked for a copy of this, all our modeling files, all our input files, all of our output files. We provided that to them on a hard drive. We've also provided it to the city, and the city can do whatever they choose with it. They can study it to look for errors and omissions. They can hire someone to look at that. They can also use it in airshed planning, because we looked at that data from a specific perspective for the project, but they can go and analyze the data in a different way to tell them things about the air quality in the city. They can also augment the model and do different things with it, and they've got all the files for free. There's a lot of work there, and they can make use of it. So in summary, I've talked about a lot of these things, but the existing air quality in Kamloops is good. Our baseline section details that in very fine detail, but when you look at the Air Quality Health Index, for example, 94% of the time, 95% of the time, it's in the lowest category or best category. By any objective measure, that's good. If I got 95 in high school, I think my mother would have said, that's good. You could have done better, but that's good. And the assessment that we do demonstrates that the project operations will have little effect on the overall air quality in Kamloops. We're not saying it's having no effect, but we're saying it's going to have little effect. We know where that effect is, and air quality is good in Upper Aberdeen, and it's going to remain good. Okay,
Okay, thank you.
any questions?
Peter, could you go back to the table in which it showed how much particulate matter was going to be coming off various mine areas? The tailings beach in particular. I don't know if that was PM 2.5 or PM 10. Yeah, I think that's the one there.
Yeah, and tailings
So you're
is-
showing 15 tons per year. Is that 2.5 or 10 or?
That's 2.5.
That's 2.5.
So most of
okay.
what comes off the tailings
Yeah.
is going to be a lot larger because crustal material tends to be mostly large particles, but there is a small fraction of less than 2.5.
Oh, so how much PM10 is going to be coming?
That's
off
all in the
tailings?
report. I chose not to highlight that here because it'd be too too confusing if I talked about 6 things at once. So it's in our
Yeah.
reports, and actually there's quite a lot more TSP from those sources because they tend to be larger diameter particles.
Okay, well, getting to my question, table E17 states the effective area in hectares for wind erosion for various mine areas. And we go to the tailings and it says 14 hectares out of a total size of 450. So I was looking for how you determined effective area and I couldn't find anything in the application. And, perhaps I just haven't come to it yet, but is there some definition of how you calculated the effective area?
Yeah, in the mine plan, we were given, the mine plan for various years, and we would have known in those years how big the area of the tailings would be, and then how much of that is underwater. And we would count the area of the tailings beach.
Well, the tailings beach is 450 hectares. The tailings pond is 100 hectares.
Now
According
it
to the
is.
tailings data.
Is that the number like in
That's
the
from
very
the
latest?
tailings facility design. 450 hectares for tailings beach, 100 for pond, and 200 hectares for embankment. And I don't know if that embankment includes the waste rock buttresses. But you've also calculated those in here as well, I see.
Yeah,
for the-
I know one thing that has changed, and this happened post-modeling after all of our work was done, and they went to a thickened tailings. Our model considers the previous version where there was a larger area that was covered with water, and so after they made the decision to change to a thickened tailings, the area that's actually flooded is now smaller, and the area of the beach is bigger, and that's part of the issue with doing this work is that at some point we have to stop taking changes into account because it takes time to run the model and do all the post-processing and then do the report. So certain things changed after kind of our deadline for all of our information for inputs.
But you mentioned like the 15 tons of PM 2.5 from the tailings. Now, is that with the best mitigation?
Yeah.
But you're not sure what mitigation they're going to use. They have to achieve that.
They've committed
that's,
to
that's more
a
of a
level.
goal then, isn't it, rather than an actual potential number? Because
Oh,
what is the base case without any mitigation? In other words,
Yeah, it's a commitment, and we didn't model a case with zero mitigation because that's not going to happen. So we model scenarios that actually can happen, which is them committing to mitigating and then following up on their commitments, which the ministry will enforce. So it's kind of a waste of resources to model a case where there's no mitigation because that's actually not real. That's not going to happen.
And what sort of emission factors did you use for that? Did you use the EPA emission factors?
Yeah, all of our emission factors come from AP42, which is what modelers call it. AP42 is the compendium for emission factors that the United States EPA maintains. So what they do is they compile the results of thousands of studies and they provide them in a form where we can go in and we're given a methodology for calculating our emissions, and then we're given factors that we can use to apply mitigation so they'll define what is the highest level of mitigation, what is a moderate, and what is a low level of mitigation. So we used all of those emission factors to drive the model.
And they come with various ranges of reliability too. because I
You've
know
done
that
some reading, yeah, they do.
The crushing one, which is in your report, says that the rating is E, which is poor. I don't know what it is for the tailings. I'm curious to know that one.
Yeah, and
But
we're
perhaps I've asked too
digging
many
way into
questions.
the
Thank you very
details,
much.
but we can answer that question if you pose it in an IR.
We have some time after the break between the switches, so I'll encourage you to come up. So is there another question? Dr. Takahashi, I see you there.
Thank you very much for your presentation. My name's
Thanks.
Jennifer Takahashi. In terms of fugitive dust, and it sounds like what you're saying, the take-home message is that's a bigger contributor to PM 2.5 than SAVE, and it sounds like even the blasting. But with your modeling, can you please describe for us the modeling, say, in the summer versus the winter? Because one thing about Kamloops is we're hot. And in the summer, we can be hot for days and weeks at a time, and we're also a semi-arid desert. And I know just from being a person who might get water from the sprinklers onto the driveway, which could simulate, rock, is that you might have so-called mitigate and have water on something, but boom, it's gone, it's evaporated. So please tell us more about the modeling, worst case scenario, hot, dry, windy summer.
Okay, so the way we run the model is we've assumed that we've calculated the emission rate as per AP 42. We apply the mitigation, and we apply that factor to that source, like say it's a roadway. And we will apply that factor to that road for every hour of the year. So the differences we see between summer and winter are just the differences in dispersion, because it's the same emission rate all the time. So in the wintertime, we see higher concentrations because wintertime is when there's poorer dispersion. There's less sunshine, there's less buoyant air to mix the air up, so you tend to get less dispersion in winter than summer. So that's what we see, is we see less dispersion, higher concentrations in winter than in summer, but we have applied the same mitigation winter and summer. So they're going to be more challenged in the summer because of evaporation, that's for sure. And that's something they've committed to.
And then another question is, I was just at the human health, summary presentation, and I learned that of the 14 metals that are being looked at in terms of the toxicology effects, that cadmium wasn't included, and yet for many industrial operations, including New Gold, they will list on the National Pollutant Release Inventory what their cadmium output is. Cadmium is occurring in the ground, gets released. Can you just help describe why it didn't end up making the list, especially since cadmium is one of those metals that gets in the air, gets on the water, gets in the soil, gets taken up by roots, gets into vegetation, gets eaten, and then goes through the body, ends up in the kidneys and in the brain. So in terms of an actual physiological human health impact, it's important, and yet it didn't make the list. So just can you tell us about that decision making?
Yeah, good question. We went through a process between the human health and the air quality people as to what we were going to characterize for them, and that decision lie with the human health people. They gave us their list, and we provided the output for them to use. So this was their decision, and what they did was we looked at 4 sources of information. One thing we've done in this study, which I don't see has ever been done in a mining study before, is we characterize each area of the mine based on the metals profile in a selection of the assay results. And this is a topic of intense interest, I understand. So the pit area, we characterized that with an ore profile. So Brian's people did some statistics on the rock that was identified in the assay as being ore, and that is what that's why we modeled the various parts of the mine separately, so that we can characterize the pit as having a ore profile concentration, and the waste rock piles have less minerals in them and different concentrations of minerals. So the waste rock piles have their own ore profile, and then same thing with the tailings. We've got samples of tailings, and so we look at the tailings, and the tailings pond has its own profile. And we also looked at metals from diesel particulate. So diesel emissions have metals in them. And Brian's team, they were the people that made all the decisions what to include in that list. And the rationale is explained in his study. So you can talk to Brian or read their report.
So I pretty much asked him the same question at the last session, and he said that the list that they got for the 14 metals to include, that I should talk with, essentially I should talk with, I was directed to talk with the chief geologist for CAM, and then they said they didn't know, and they said, oh really, actually initially Dr. Wild told me, oh, cadmium is part of the list. And then I showed him the 14 that are part of the list that was assessed, and it wasn't on there, and he was surprised. And then I was directed to talk with you to find out, because he said that you would know why it wasn't included or not included on, or included on the list. So I just want to know how that decision-making was made.
Yeah, and we've been putting together a memo for the EAO to explain that, and I believe that's been forwarded to them. So that's in their hand.
And that needs to be made public
if we
record.
need to, it's part of the public record. But if we need to detail what exactly is in each of those calculations, above and beyond what's in the appendices in the report, we can easily provide that as a supplemental matter. Like we're prepared to do that. So Brian's people did the analyses to choose the 14, and that was based on, like, we had full disclosure of all of the information in the assays.
Cheryl Flippen, thank you for your talk. Isn't it the choice of the 14 based on what was present in the assay, and then they look at the concentrations and look at the standards for health and say these concentrations are so tiny that we don't need to look further at them in terms of their potential for health? Isn't that how they kind of were able to narrow down there to 14?
Yeah, now you're really getting out of my area, because I'm not a human health risk assessment specialist.
Okay.
That's really a Brian question, but one, and I was involved in some of the early work on this. And what you also have to consider is are they things that are already there in high concentrations? Like there's a lot of metals that are already present in the Earth's crust. They're already present in the soil, and if we're not adding to it, if what we're adding is exactly what is already there, then there's no accumulation. So they have to consider these things. And I think Brian they also screened out things that have no interaction with the human body, that they're ingested and they pass through. So they're really the ones that made all those determinations. Like, look at the assay results, you got like a third of the periodic table of elements in there. A lot of them don't matter, and he chose the ones that matter.
We have time for one more question if anybody has one. Otherwise, there's a little animation.
Oh yeah, we got time for that?
I think we could probably have time for, if we do it quickly.
Okay, let's.
This makes, when I first saw it, it made sense of some of those pie charts that we had, so I think it's worthwhile taking a look at.
Yeah, the best way to explain a dispersion model and how it works is to actually just show you rather than waving arms. And as soon as that thing disappears, so January 3rd, there's the hours going by. There's the scale. The bottom here is 2.5, 7, 15, 25, 35, 45. And then the scale kind of tops out here Alberta has a standard for PM 2.5 for 1 hour, and that number is 80. So the blue that you're seeing is well below the Alberta standard. The brown is even below the Alberta standard. The very darkest brown is above. So this is the city. This is all your little furnaces chugging away in January, your cars driving to and from work. There's some industrial emissions in there, but not a whole lot at ground level. When you see the big blob, especially the brown stuff, that's a period of stagnation. So that's when we have very low wind speeds. Things accumulate in the valley bottom, and then big east wind or a big west wind will just kind of whoosh everything out towards Valley View. And there's a period here where, you know, kind of like that period we had this year from January 4th to 7th. There was almost no wind for 3 days, and we saw at the monitoring stations that pollution levels really went up. So that's kind of what you're seeing here. You're seeing these kinds of things, and this is what the model does. We model something like 27,000 hours, and we chose the worst year to portray in our work. So that's the city. That's the city all on its own. And then I can show you the project all on its own. This is what's happening on the mine site all on its own. PM 2.5 again, hour by hour, the same time period. So the first part of January, and it's fairly windy. Effects are largely confined to the mine site. Stuff is kind of going to the south, but then you'll see it kind of go to the east once in a while, penetrating a little bit of the way into the city. And then we're coming up into that stagnation period. So you're going to see that kind of grow a bit. Sometimes it moves away from the city. And then our stagnation period here. So the mine definitely does have an effect in the city. The greatest effect is near the project area. It can go all over the place. But since the winds prevail from the southwest, they move to the northeast, and the city in general, overall. A lot of exceptions to the rule. Something different happening every hour. So these are the two cases we modeled in isolation, and then this third one is both of these added together. And you can kind of see the city's doing its thing there, the mine's doing its thing. It's kind of a buffer between them. This is a period of probably pretty high wind speeds. And then we'll work into that stagnation period again. And remember again, this is the worst month of the year pretty well. We chose it because it's spectacular. If we showed you July, there would be long periods of nothing and then a blob. And then nothing and then a blob. There, that's that stagnation episode. And then it dissipates after a day or so.
But join me in thanking Peter for a wonderful presentation.
Thank you.